Okay, so it's a pleasure to introduce our second speaker for today, Duncan Dauvergne. We'll talk about the longest increasing subsequence.
Okay, yeah, so maybe I should have drawn more attention to the actual title, which is Geodesics in the Directed Landscape, and then I have a very large subtitle here for what I was going to talk about to start. Yeah, so this is, I'm going to explore one aspect of the directed landscape that Alan was talking about in a bit more detail, which is geodesic. So the first 10 minutes or so is going to be sort of heavily overlapping with things that Alan was saying, but it's good to recap, especially to recall some of the particular facts about the directed landscape that will come in later. So just to kind of start with a concrete theorem, I wanted to come back to longest increasing subsequences. So again, just to recall, so we have a permutation, sigma, and a longest increasing subsequence is just a subsequence of maximal length. So for example, 4, 5, 7, like this. And the length here, I'm going to call Ln. So in this case, Ln equals 3, or this is n equals 7. And we can also think of the subsequence itself as a function from the set 1 up to Ln into the numbers 1 through n. So in this case, we would have In of 1. So the first point is 4. In of 2, the second point is 5. And In of 3, the third number we see, 7, or something like this. Okay. And so just to kind of recall the main theorem about Ln, this is the well-known Weikdijk-Johansen theorem. Which says that if Ln is the length of the longest increasing subsequence in a uniform permutation with n elements. So,
excuse me, you keep saying the longest. I mean, you have In is not defined by the length, right? Because you can have different longest possible.
Yeah, so yeah, this is a good point, and I was kind of glossing over it a little bit. Yeah, so for example, in this permutation that I drew, we also have this one 3, 5, 7. So for the purposes of what I'm going to say, we can really
7. What?
4, 6.
Also 4, 6, 7.
Yeah, also 4, 6, 7. Yeah. So for the purposes of what I'm going to be saying, we can choose In arbitrarily from among these subsequences. So when I sort of get to this next scaling part, maybe I'll write this down more formally as a remark, but the distance between, this is something Balint mentioned, the distance between any two of these subsequences in the scaling that we're going to take is going to go to 0. So the issue of which one you choose is not so important, just for the purposes of this talk. I mean, again, there are interesting questions in this direction, but not for, scaling to the directed landscape limit. Okay, so if, so as I was saying, if Ln is the length of the longest increasing subsequence, so we can talk about the length, even though we can't talk about the subsequence, then we know that Ln is equal to 2 root n as the leading term, plus n to the 1/6 times yn, where this yn, this fluctuation term, converges to a Tracy-Winham GUE random variable. So this is one of the marginals that you see in the directed landscape. And then our theorem that Balint mentioned is concerning this In. So here, I'll let In be any longest increasing subsequence in a uniform permutation So then if you rescale IN appropriately, it converges to a random limiting function. So if I look at IN of, so IN, the domain of IN is roughly the numbers 1 through 2 root n. So I'm going to look at IN at the point 2 root n times x. So these x values can range roughly between 0 and 1. And I subtract off the mean term, which is nx, and rescale. Then this converges in distribution to a random function pi of x. So this is here, pi is a function from the interval 0, 1 to r. And the underlying convergence here is functional convergence in the uniform topology. So one way of saying this is there's a coupling between all the left-hand sides and the right-hand side such that the left-hand sides converge uniformly to the right-hand side as functions on 0, 1. And just to address this point about if there are two different longest increasing subsequences, so if Jn is any other longest increasing subsequence, then the sup over x of In of x minus Jn of x, if we rescale by n to the 5/6, then this is converging to 0 in probability. So on this scale, it doesn't matter which exact subsequence you're looking at. Okay, and so something that Balint mentioned is that this pi is a special function called we call the directed geodesic. So this is a geodesic in the directed landscape, and it also rises as the scaling limit of, for example, geodesics in last passage percolation. That's how we kind of first came upon this object. It's also somehow closely linked to limiting trajectories of second-class particles in TASEP, which is something Balint mentioned at the end. And this whole talk is really going to be about exploring certain properties of this object, which we feel is quite fundamental and has really interesting properties. So of course, in order to talk about the directed geodesic, you need to understand the space in which it's coming from, and this is the directed landscape. And so this is kind of my recap on certain things that Balint said. So what is the directed landscape? So just to recall, it assigns distances between pairs of points x, s, and yt with s less than t. So it's assigning distances to pairs of points in the plane. So for example, maybe I put my xs down here and my yt up here. And it's important that the time coordinates, so s and t, are ordered in the right way here. So we always have s less than t. So this is the parameter space, which we call directed R4. It's the space of all x, s, y, t, where s is less than t. Okay. And then if you just look at the single point of the directed landscape, then up to this factor, which is essentially the rescaling of the Euclidean metric, as Balint mentioned, you see Tracy-Whittam GUE random variable. So this is the shadow of that Bike-Deft-Johansen theorem. Some other good things to keep in mind: it's continuous. It has scale and shift invariance. So I won't write down the specific invariances, but they'll come up a little bit in the talk. It has a nice independent structure. So I say here that it has independent increments. So what do I mean precisely by this? Is if you look at two strips, say here and here, or any number of strips, but we'll do this with two. then all of the distances that L assigns in these two strips are independent. So somehow you can think of this as measuring distances according to some very rough, rough independent underlying noise. And we can't describe the noise precisely, but because we're only allowed to move forward in time, if you assign distances, if you look at distances between two areas that are disjoint in time, the independence of the noise means that those two distances can't interact, and you see independence there. Okay, and in terms of working with L, so something Balat mentioned I wrote down here, which is that it satisfies a triangle inequality, but it actually satisfies something which it satisfies something more, which we call a metric composition law, which is going to be very useful for our purposes. So what is this? Let me try and erase some of the things that I drew in the picture. So say I fix times st and I fix some time r in between. And I want to find the distance in L between x, s, and yt. So we're going to think of this as, we're thinking of this as a metric. And so we're imagining finding an optimal path between these points. And because we can only move forward in time, this is what our path is going to look like. It's essentially going to look like a function of this sort. And it has to choose some point at the time r to move through, which is optimal. And so this is what this metric composition law says, is that to go from xs to yt, we pick the maximal z in r such that that maximizes L of xs zr plus L of zr yt. So you have a similar law with the usual metric, but again, everything is kind of reversed in the directed landscape. So we have a maximum here instead of a minimum. Minimum is what you would usually expect. You're trying to minimize distance among all paths. Okay, and then we can define, again, as Balat mentioned, we can define geodesics in the directed landscape. So how do we do this? So say I have a function pi going from st to r. And I'm just going to use this notation pi bar of r to be equal to the point pi of r comma r. So we say that a function pi is a geodesic if the landscape distance between the starting point pi bar of s and the starting point pi bar of t. So maybe let me try and draw this picture. Is the same as, basically this equality is saying that along geodesics, the triangle inequality is always inequality. So no matter how we break up the geodesic, so into k pieces, if I sum up the distances along the geodesic, then I just get the distance between the two endpoints. So the analogy of what happens if you do this with a straight line in Euclidean space. And you'll notice one thing that's kind of important to keep in mind here is that you might think we're working in the plane, so a geodesic should be a curve in the plane. But we have, because we can only move forward in the time direction, it makes sense to think of a geodesic as a function of one variable rather than a function of two variables, where you're thinking of the curve in the plane then as being the graph of the geodesic itself. And so these pi bar of r's are points on the geodesic. Okay. So that was hopefully mostly recap. And then we can say many things about geodesic. I'm just going to focus on the geodesic between 2 points in the directed landscape. So because of various shift and scale invariance considerations, all geodesics are roughly the same. So I'm just going to focus on one of them. And so this theorem says that there is a unique, or maybe I should say almost surely, there exists a unique geodesic pi from 0, 0 to 0, 1 in L. Okay. This is again from the paper with Janos and Balint, where we constructed these objects first. And this pi, which is a function from 0, 1 to R, is the scaling limit of the longest increasing subsequence. So this is the object that came up in the first theorem. And it's also the scaling limit of various other things. Okay. Now I wanted to, obviously we're, my talk plus Balint's talk, we're kind of saying a lot about these objects. So I thought it would be good to at least have one fairly concrete proof here. And this theorem itself, actually, given the facts that I've said so far, you can, with this plus another couple things about the directed landscape, you can really give a proof of this theorem. So I'm going to basically go there. I'm going to need two more facts about the directed landscape. So to prove, let me move out of purple. To prove this theorem, we actually just need two more facts about L, which are good to keep in mind for thinking about this object as well. So the first one is that if I have any, yeah, sure, okay. So for any t not just greater than 0, but t between 0 and 1, the functions L of 0, 0 dot t minus, say, 0, 0 up to 0 t, and L of dot t 0, 1 minus L of 0 t 0, 1 are locally absolutely continuous with respect to Brownian motion. So what are these functions? So say I look at my directed landscape, I have the 2 points 0, 0 and 0, 1, and I have some dividing time t. And if I look at distances to this line, and I sort of vary the points back and forth, either starting with 0, 0 or starting with the point 0, 1, then what I see locally is just a Brownian motion. So this is something that was mentioned in Balint's talk. This is coming from the fact that these processes are actually parabolically shifted Airy processes. So they're the top line of this Airy line ensemble of non-intersecting Brownian motions. And this local Brownian structure is really one of the ways we can access, one of the key ways we can access the directed landscape. And the second claim is just actually in some sense, a strengthening of this parabolic shape theorem from just a single point distribution to multiple points. So we have this shape which says that there exists a constant c greater than 0, such that for all u equals xs yt in our given parameter space, L of u minus its essentially expectation of x minus y squared over t minus s is no bigger than this constant up to, some log factor. But essentially you can think that L is going to be close to this parabolic shape. And so the randomness is fairly small. I'll say with both of these theorems, we can have much more refined versions of these. So there are nice quantitative estimates available on how locally Brownian L is, and other types of things which are locally Brownian in L, and more refined versions of the shape theorem. But just for thinking about existence and uniqueness of geodesics, these two things are going to be enough. Okay, so let's attempt to put together a proof. And maybe I should say, this proof is not particularly hard or deep even, but I think it kind of nicely illustrates all the different things that come together when we're working with the directed landscape. So you get to use metric composition, you get to use this local Brownian structure, you get to use the shape theorem, all of these things kind of come in. So how are we going to approach existence? So I'll first construct a geodesic on, or first construct a geodesic on dyadic rationals through sort of a recursive construction. So I'm going to define pi1 just from the points 0, 1 into R by setting pi1 of 0 equal to 0 and pi1 of 1 equal to 0. So remember, we're trying to construct a geodesic between the points 0, 0 and the points 0, 1. So we're going to need to do this. And then how does the recursion work? So given a function, given the sort of kth iteration, which is going to go from 2 to the negative k z intersect 0, 1, so dyadic rationals at scale k to R, we can define the next level, so pi k plus 1, as follows. So 2 to the negative k plus 1 z. So first, we're going to set pi k plus 1. So I set pi k plus 1 equal to pi k on their, my writing's getting a bit messy here, on their shared domain. And then we need to fill in the gaps to define pi k plus 1. So essentially, what have we done here? Pi k, say, defines us on all of these black lines. And then we need to fill in the gaps, one between every one of these black lines to define pi k plus 1. So how do we do this? So for t not in 2 to the negative kz, I'm going to set pi k plus 1 of t to be equal to the argmax of a particular function. So there might be many argmaxes. We're going to be able to choose one arbitrarily. So this is going to be L of pi k of t minus 2 to the negative k plus 1. Up to zt. So there's the argmax over z and R. Plus L of zt up to pi k of t plus 2 to the minus 2k plus 1. So what is this formula saying? That it's kind of doing the obvious thing. So if we know our values on two black lines and we want to define our value at a purple line in between, we just maximize over distances, over sums of distances going from black to the x and then the x back to black. And then the key point is that each pi k satisfies this equation. So this, maybe I'll call this like the geodesic equation. So each one of our pi k's satisfies the geodesic equation on dyadic rationals because of this metric composition law. So we had this property here, which said that if we maximize over fixed point over a fixed time r, we maximize over z, then we just get the distance between x, y, and st. So we're just iterating the metric composition law, and this tells you that we satisfy the geodesic property everywhere. So each pi k satisfies the geodesic property on dyadics. And then basically you can extend to a limit from all dyadic rationals to R. So this limit I'll call pi infinity. And this, then you can hope, okay, we should be able to extend by continuity to a function from 0, 1 to R. And this you can do by this shape assumption. So the fact that we satisfied this geodesic equation tells you that none of the individual increments should be able to be too small. So the geodesic equation tells you that, plus this sort of shape assumption saying we can't differ too much from a parabola, tells you actually that your limit on dyadic rationals has to be Holder 1/2. So pi infinity, and this must be Holder 1/2. And hence extends to a geodesic. From 0, 1 to R. So this is, I think that this illustrates a decent amount of the things that come in here. So we're always using, when working with the directed landscape, you have this kind of shape assumption that you're always keeping in the back of your mind. And metric composition is the key kind of extra geometric property which actually comes in. Okay, so how would we, this is existence. Uniqueness is actually a bit easier. So uniqueness, basically by continuity, it suffices to show that for every fixed t between 0 and 1, that there exists a unique argmax of the function L of 0, 0 zt plus L of zt 0, 1. So let me explain this a bit more. By the metric composition law, our geodesic has to pass through an argmax of this function at every t. Okay. And sorry, I haven't said where I'm actually using continuity yet. So continuity allows us to go from not just every fixed t to every fixed rational t. And so we can think about what this function here actually looks like. And this is going to be, it's useful here, but it's also going to be useful to keep in mind later. So what is this? Well, each of these locally just look like Brownian motions. So these are essentially, a good way of thinking about these objects is these are Brownian motions, but they also have some parabolic shape. So they're locally Brownian, and then they sort of decay parabolically as you go off to infinity. And so because of this parabolic decay, any argmax is going to be contained in a compact set. And then once you've restricted to a compact set, you're just adding two independent Brownian motions because they're coming from independent parts of the landscape. And so you get a unique maximum. So basically the sum looks like a Brownian motion. And so it has a unique argmax on every compact set. And so this is kind of the last thing. This is the last thing that comes in, and this local Brownian property you can explore it more and more to get a more refined understanding of what's actually happening with these geodesics. Okay, so this was a fairly simple theorem, essentially, just about existence and uniqueness of geodesics. Let me say some kind of deeper properties. So what I said so far, I just showed that geodesics are holder 1/2 continuous. In fact, you can do much better. They're holder 2/3 minus, and we have an explicit modulus of continuity. So let me just write this down. So there exists a random c greater than 0, such that for all s less than t in the interval 0, 1, pi of t minus pi of s is bounded above by c times t minus s to the 2/3 times a log power of 2 over t minus s. So hopefully this, what I've just written is a little bit reminiscent of Levy's modulus of continuity for Brownian motion. So it's really the same type of theorem. And in fact, you have, maybe I'll mention that you have some tails on C as well. So C has like e to the negative m cubed tails for some constants C and D. And really the proof structure is kind of the same. You have essentially a scale invariant process, and the proof of Levy's modulus of continuity for Brownian motion gives you a very similar structure, gives you a modulus of continuity for geodesics, which also shows that they're kind of starkly different from Brownian motion because they're almost holder 2/3 instead of almost holder 1/3. And another thing which Balint mentioned is that, you know, just like if you take a Brownian motion or an object which is absolutely continuous with respect to Brownian motion, and you scale around a point, you're going to get a nice, with Brownian scaling, you get a nice scaling limit, which is, you know, Brownian motion in this case. And you have a similar theorem with directed geodesics. So I'll fix my points S in 0, 1. So then the function pi of S plus epsilon cubed t minus pi of S, when rescaled by epsilon to the -2, this converges in distribution as epsilon approaches 0 to some limit gamma of t. So this convergence in distribution should be thought of not for a fixed time t, but this is convergence in distribution as functions going from R to R. So here gamma is a function going from R to R, and we should think of this as the bi-infinite geodesic. So what is this theorem doing? Is it's taking a geodesic, we're fixing some point. It doesn't matter what point we choose, and scaling. And in the limit, we get some interesting bi-infinite geodesic in distribution. The only, the one caveat I should say here is it's important here that I chose S to be in the open interval 0, 1, and that I excluded these two endpoints. So this is somehow a real difference between geodesics and like a Brownian motion, say, is that we expect, and this is really decently conjectural, we expect the behavior at the endpoints to be much different from the behavior in the middle. So if you zoom in this scaling at one of the endpoints, you still get a scaling limit, but it's not a bi-infinite geodesic, it's just an infinite geodesic. So it's a much, it should be a much different object. So in practice, distinguishing between these two, it's not clear. And I'll mention something to that effect later. So we have two kind of Brownian motion-like theorems. We have this modulus of continuity, we have a scaling limit, and now we have a third kind of Brownian motion-like theorem. So just like you can study quadratic variation for Brownian motion, so quadratic coming from the fact that in some sense they're going to be holder almost 1/2, Here we're Holder almost 2/3, so instead of studying a quadratic variation, you can study a 3/2 variation. So this is another result. So these last two results are from a newer paper with myself and Shirav and Valant. So I'm going to define the 3/2 variation as follows. So let me define V 3/2 epsilon. So this 3/2 variation at scale epsilon of a function f. So here f is a function from 0, 1 to r. And I'll define this as the sum over u in the interval epsilon 1 and on the grid epsilon z of the increment of f from u minus epsilon cubed raised to the power of 3/2. Okay, so you can do this with the directed geodesic pi. And then what you get is that as epsilon goes to 0, this converges in probability to a deterministic constant nu, which is given by the expectation of gamma of 1 minus gamma of 0 raised to the power of 3/2, where this gamma is the bi-infinite geodesic we introduced up here. So I'll say a little bit more about these things. So this first, maybe just before I launch into trying to explain what this gamma is, this first theorem is essentially pretty easy. Like I said, it's not much more than the proof that I stated above, plus some Levy's modulus of continuity type ideas. This second one is also somehow, for the most part, the things that you would expect to work once you understand what's going on work. And this 3/2 variation is actually somehow, unlike in the case of Brownian motion, there's a lot more involved to actually getting a 3/2 variation. So you need to do some more delicate moment bounds, and you need to extract independence properties of this directed geodesic, which aren't particularly obvious. And one consequence of the fact that this is a hard proof is, unlike with Brownian motion, it's not clear, or it's not easy at the very least. We weren't able to do it, or we weren't able to do it on our first go through. It's not clear how to extract an explicit sequence of epsilons going to 0 for which this convergence is almost sure. So you'd hope that maybe if you set epsilon to be like, if you set epsilon to be, say, 2 to the negative k, so you're taking a 3/2 variation on dyadic rationals, that this would converge to 0 almost surely. But this is somehow future work, something we don't know how to do at this point. So let me explain a little bit about what this gamma of t is. This is really, and the key here is going to be exploiting the local Brownian structure of the directed landscape. So what is gamma? So let's think about what happens if we take a geodesic and zoom in around the point S. So I have around my time S. So I have my time S. I have the time S plus epsilon cubed. And the way that I choose these 2 points, which are, I'll call, say, X and Y, is I'm going to be, if I think about this metric composition law, I'm sort of going to iterate the metric composition law and do a maximization problem over 3 objects. So X and Y maximize the function L going from 0, 0 up to XS, plus L going from XS up to Y S plus epsilon cubed, plus L going from Y S plus epsilon cubed up to 0, 1. Okay. So maybe I'll call this first function A1 of X, just to kind of keep it simpler, and this second one A2 of X. So we can think, okay, what's happening here? So all three of these objects are independent because they're happening in disjoint time intervals in the directed landscape. So I have three independent objects that I'm maximizing over. I have two of these objects. So this last one should be A2 of Y. I have two of these objects which are essentially Brownian motion. So this A1 of X, this A2 of Y, these are locally Brownian. And what about this object in the center? So this is a much more complicated thing to understand. But it's really, this is the directed landscape in a very small strip. And so from the purposes of this maximization problem, it's not going to matter all that much at the first scale. So you should think of this roughly negative x minus y squared over epsilon cubed. So when x and y are far away from each other, it's going to give you a very negative value, which is bad for our purposes. Plus a fluctuation term, which is actually in this case of order epsilon. So we've got a very small fluctuation term. So if we're thinking about where this x and y are, essentially they're going to be near the maximum of A1 plus A2. So here's the idea, is that this x and y are near the maximum of A1 plus A2. So A1 plus A2, again, we're summing independent Brownian motion. So this is essentially itself a Brownian motion. So if we decompose, if we look at this process near its maximum, it looks like a point, and then you subtract off a two-sided Bessel free. So this A1 plus A2 near its maximum, which I'll call capital Z, it looks like maybe negative R, where R is a two-sided Bessel III process. And then A1 minus A2, so if these were Brownian motions, then A1 plus A2, A1 minus A2 are independent. So this process near Z looks like an independent Brownian motion. Okay, so the upshot of this construction is that what does our maximum look like? We have, you can imagine that you have curves here and here, which look like differences of independent Brownian motion and Bessel process. And then you have some strip of directed landscape in the middle. Okay. So the more precise statement would be, you know, if I look at A1 of Z plus, say, epsilon squared Z, and I rescale, I do the same thing with A2. And I do the same thing with my strip of landscape that I saw in between. So there's a lot of funny epsilon squared, epsilon cubed terms coming in here. And this is just because of the funny way that the landscape rescales. So this first one is roughly negative R plus B over 2 of Z. The second one looks like negative R minus B over 2 plus Z. And this third one on this scale is actually equal in distribution to just a strip of directed landscape itself. So we have, this is this scale invariance. So it's sort of coming from a scale and shift invariance. So here, where R is a vessel, free, and B is a Dauvergne motion. And this, so this is the rescaling under which we're going to see this bi-infinite geodesic. And so now we kind of have the tools to build gamma. So there are two things. What does this bi-infinite geodesic look like? So gamma is scale invariant. So it suffices to look at gamma restricted to the interval 0, 1. And on the interval 0, 1, gamma is a geodesic in L that maximizes negative R plus B over 2 of gamma of 0 plus L of gamma of 0 comma 0 and then gamma of 1 comma 1 plus negative R minus B over 2 of gamma of 1. So in some terminology, you think of this as a geodesic weighted by initial and final conditions. So you sort of have this, to construct this bi-infinite geodesic, you look at a strip of landscape and you impose a certain initial condition and a certain final condition, and you're maximizing over all geodesics in between these two. You're choosing the geodesic, not just the geodesic between two fixed points, but a geodesic now between two random points. Okay, and so somehow this is somehow a much different object than a geodesic between two fixed points. But it's because we understand, because we only understand certain marginals of the directed landscape, it's actually not too clear in what ways it's different from a usual geodesic. Though by the description, it seems like it should be fairly starkly different. Okay, so that was kind of all I wanted to say in terms of theorems and such. I thought I would end by mentioning a few things that we're still thinking about regarding geodesics. So these I sort of loosely think of as, these are essentially open problems. So the first one is related to the fact that we have this strong belief that the geodesic is different at the start than in the middle. So we believe geodesics are different in the start and the middle. So maybe I'll phrase this first open problem as a fill in the blank. So maybe I'm going to fix t between 0 and 1/2. Fill in the blank. Of course, you can sort of ask more sophisticated questions here, but just what is the difference between the expectation of the absolute value of pi of t minus pi of 0 and the expectation of pi of t plus 1/2 minus pi of 1/2? So the question is, does this box equal less than, equal to, or greater than? So, you know, you can come up with some loose heuristics about thinking of the directed landscape as some mountainous terrain, and you start on some hill and then you sort of slide into a valley. And so in the middle of the geodesic, you're kind of moving along in this valley. And so maybe you need to move a little bit further afield to get down from the hill into the valley, or maybe once you're in the valley, you're allowed to move further afield. I don't know, it's not clear, and we haven't done simulations for this particular question. Another one that I like is this is sort of a hidden information question. I'll give a couple of these. I quite like these ones. So first, I'll phrase these ones as conjectures because we're pretty confident, conjectures / questions. I believe these things are true. So conjecture, there exists a function f such that f of pi equals L of 0, 0, 0, 1. So what do I mean by this? Pi is the geodesic from 0, 0 to 0, 1. And L is the distance in the landscape from 0 to 0 to 0, 1. So this is saying that if you just look at the shape of the geodesic, you should be able to, from the shape, determine the length, which is not at all obvious. But you know, heuristics suggest that this sort of thing has a chance of being true. A second conjecture is a little bit weaker than this first one. And for this, I'm going to let A be the set of all geodesics in L. So say I had access to the information given by every single one of the geodesics. So I see all of the shapes. Then there exists a function G such that G of this entire set equals the directed landscape itself. So if you see all of the geodesic shapes, then you can reconstruct the entire metric. So it's clearly a little bit weaker than the first conjecture, because the first conjecture says given one geodesic, you can construct its length. So if you know the length of every single one of your geodesics, you clearly know all distances in the landscape. But conjecture 2 might be slightly easier because you can look at things like correlations between different geodesics in order to help determine information in the landscape. Okay, so it's coming up to, well, 10 o'clock my time, so I will go ahead and stop there.
Let's thank the speaker. Any questions?
Hi, can I have some comments or questions on question 1? Just in these last slides, I might on Balázs. So in last passage percolation, we have this machinery with Offer, Bussani, and Timo Sepalainen of comparing point-to-point geodesics with stationary geodesics, and those kind of give some bounds on one in terms of the other. Okay. Do you think that can be useful here?
I think it might be. Yeah, this sort of thing might be useful. This first question we haven't thought about that much, and I don't know, but I think there should be a way of passing to the limit in this case. Yeah. I think that there are some genuine, differences with. There might be some technical issues with going from the finite version to the limit, because somehow, but I'm not. What might be a little less clear is how much of sort of the pre-stationary phase passes to the limit when you're looking at the geodesics. But I think it would be useful, yeah.
Okay, I guess some kind of a stationarity can be done directly in the limit. Is that true?
It's not something we've thought about, but I'm not sure if you could do it directly in the limit, but you could probably pass through to the limit even if you can't do it directly. I think this sort of thing should be doable.
Okay, thank you.
Sorry, f is function and pi is function. What is f of pi? Is it number or function? What is it?
Yeah, so I mean, I was a bit loose. So like f is a function whose domain is the space of all continuous functions from 0, 1 to r.
Mm.
So it's with these conjectures, I was a bit loose about stating the domain. But basically, one way you can think about this is there should be some statistic you can measure about the geodesic pi, which allows you to reconstruct the length. So one reason why you might think this is reasonable is, say I give you a very small amount of information about the geodesic. I just give you its location at the halfway point. So if its location at the halfway point is somehow, I think, very far to the one side, then I think it's the case that then you know the only reason you would go very far to the one side would be if there was a really good weight over there to that one side. So I think if, you know, a geodesic at the halfway point deviates far to the one side, then you expect its length to be slightly longer than otherwise. So if you sort of measure enough of these statistics and, you know, use the full geodesic itself, I believe you can construct the entire length.
Thank you.
Any more questions? If not, let's thank both our speakers of today. See you all next week in the usual time, I think. Right? Okay, good.